Okay, in this problem, I've got a Brayton cycle with a regenerator. Okay, so it's a regenerative Brayton cycle, and what the big difference here is we're going to use a cold air standard where we use constant specific heats. Now, again, I'm not a big fan of using constant specific heats, but sometimes we use them where the specific heat ratio is 1.4, and then my specific heat that I use for delta H, which is Cp, is 1.004. Okay, so it tells me that the pressure and temperature at the compressor is given here. This is on the back side of the compressor. Okay, then it goes through a regenerator. Okay, and the temperature comes out here. Okay, then it goes into the combustor. Again, the whole idea of generator is to make the combustor not work as hard. Okay, then put it through the turbine. Okay? And then the hot air comes out of the turbine and goes back into the regenerator using this hot air to heat the air over here. So again, the generator does not have to work as hard. Using the cold air standard, all I need to do is find my temperatures because my delta H's then are Cp times delta T. So we'll go ahead and find our temperature. So this is the compressor right here, and the compressor is isentropic, therefore it's adiabatic. Okay, and then for constant specific heat, again, if you remember, we talked about this with polytropic process. For an adiabatic process, the temperature ratio is related to the pressure ratio given by the following equation, to the K minus 1 over K. And again, this is going back to the polytropic conditions for an ideal gas with constant specific heat, okay, which is the last section in chapter 3, if you don't remember that. But because I know that pressure ratio, because I know the specific heat is standard, because I know it's adiabatic, I can use this to calculate T2. Okay, again, you want to make sure you use absolute temperatures, and I can find that T2 equals 556.7. Okay, and I'll do the same thing for the turbine over here. Okay, turbine is 3 to 4 right here, so I can say, okay, same idea, T4 over T3 equals P4 over P3 to the K minus 1 over K. And again, because it's an ideal gas, because it's constant specific heat, and because it's adiabatic, I can use that. Okay, and then from that, I can then calculate what T4 equals, and I find that T4 is actually 710.7. Okay. Now the other thing that I have, okay, I'm going to bring the picture up just really quickly on here. Okay, so again, what we're looking at is right here with the regenerator. Okay, and again, we've got this kind of preheating. We've got the hot exhaust coming out. What's coming in through the compressor? I basically preheat that before it goes into the combustor. In an ideal case, which is what I have here, I have this ideal regenerator. The temperature here is the same as the temperature here, right? Basically, I bring that temperature all the way up to the exhaust temperature, saying that T4 is the same thing as Tx. Okay, and that's for an ideal regenerator, which is what I have here. So what I know then is that Tx equals 710.7 K as well. And again, because the regenerator is ideal, okay, because basically my regenerator efficiency is 1, okay, where I've got this ideal regenerator, okay, those temperatures are going to be the same. Now that I have those two temperatures, okay, I can go ahead and calculate what it is I'm looking for, which is the thermal efficiency, okay, which is going to be the compressor and the turbine. So my thermal efficiency, okay, is going to be Cp times delta T of these things, where I've got my turbine, which again is 3 to 4 here, so that's going to be T3 minus T4 minus the compressor, which is going to be T2 minus T1, again, all times that constant specific heat. And then that's going to be divided by Q in, which is going to be Cp times delta T of the combustor, which is x to 3. Again, typically I go 2 to 3, and I'd get, a temperature increase of about 800, but because of what I have here, I only have a temperature increase of 650 or whatever. Okay, So that's the temperature change that I use now. Again, because I basically use the hot exhaust to bring that temperature up. And again, ideally, I can bring it all the way up to the exhaust temperature for a perfect system, which is what I have here. So T3 minus Tx. And that will give me, knowing all of those temperatures, that will give me my thermal efficiency, which I get to be 59.5%. Okay. So again, with the cold air standard, all I need are my temperatures. I can do the isentropic or adiabatic using what we know, what we've learned about polytropic processes back in chapter 3 of an ideal gas. And then with that regenerator, again, I basically preheat what comes out of the compressor to whatever is getting exhausted out so that my combustor doesn't have to work as hard. I don't get as much of a temperature change here, so my Q in is lower, thus improving my thermal efficiency.